So today I thought I'd give a lecture on a particular volcano topic that is of extreme interest to a lot of Americans, and it's what in part ignited my passion about volcanoes. Specifically, Mount St. Helens, 1980, May 18th, an eruption which inspires a generation of geologists to study volcanoes. And so I figured I'd give that lecture because a lot of people do not understand exactly what happened in 1980. Even some of the people that lived through it, they understand the nuances of the politics and all of the other things that went around with it, but not necessarily the science. So I wanted to talk about what Mount St. Helens meant for us, what it meant for the science of geology, what it meant for the new burgeoning science of volcanology, studying volcanoes, which is what my specialty was when I was in graduate school. And I want to give a lecture here. This is because as co-owner of Blackland Geology and Reptiles, I put a note to my Facebook page saying, hey, I wanted to test out to give a lecture on some random topic. Is anybody interested? And Mike McConaughey, one of the respondents, said, hey, why not volcanoes? And he made a pun about volcanoes being hot or something like that. So I figured I'd give a lecture on volcanoes. So I'm going to share my screen here. We're going to do this Zoom, but then I'm going to post it to YouTube. So hopefully this thing works. So, random example. I am based in McKinney, Texas, and based in McKinney, Texas, I figured let's put up a picture of McKinney, Texas, and you're going to see why this is here. So this scale here, if you can look at the image, the scale bar in the lower left-hand corner, this is about 5 by 5, 5 miles by 5 miles on the side. So this is the main mass of McKinney out to the airport, past the college, out to almost Custer Road. 5 by 5 is 25 square miles. When Mount St. Helens failed, it underwent what we call a debris avalanche. And we knew very little about debris avalanches at the time. It was a relatively new phenomenon. What does that mean? That doesn't mean that other volcanoes had not done this before. It meant that we hadn't really understood what these volcanoes had been doing in the past. We had seen deposits around old volcanoes, and we didn't know exactly what we were looking at. And then Mount St. Helens did its crazy thing, and it produced a massive failure of the side of the volcano, and it covered a humongous area. Whenever we talk about massive areas in geology, it's hard to wrap our heads around them. So using a city as a scale, a city of 200,000 people as a scale, 25 square miles, let's talk about debris avalanches in general, and then specifically dig in to Mount St. Helens. So I posted this, I've taught this before in classes. In about 7,500 years ago on the Chilean-Argentinian border, a volcano known as Socampa failed, and we can see the volcano right here. The volcano failed about a 70-degree section of the volcano, and it broke out, and debris covered a huge area, roughly outlined by this black line. It covered such a large area that McKinney, 25 square miles of McKinney, is shown here. Once when I was presenting this to a group of people, one of the students said, well, the town, if that's McKinney, the town southeast of McKinney is Wiley. And I said, yes, Wiley, Texas, the great volcano of Wiley, Texas. It's one of those fun geography. They were thinking about it, and then they went, so that's why Wiley's located here. We can see here that we have this massive volcano, crater at the top, lava flows which extend out from the sides, and they're juxtaposed against material of different composition, which is why they're different colors. And this volcano failed on the side, and it was associated with a small eruption. The reason why they think this particular volcano failed is because the volcano was built along a fault, and the northwestern section was on the lower end of the fault. The southeastern section was on the upper section of the fault. And as the fault moved, the volcano became gravitationally unstable and failed to the northwest. So how does this relate to Mount St. Helens? Well, we had seen this back in through the 70s and early 1980s. We'd seen this in the border of Chile and Argentina, but until Mount St. Helens failed and we saw this kind of behavior in real time, we didn't really know what we were looking at, nor could we make any claim about, or a really good claim about how it happened, all right? So let's talk about Mount St. Helens, May 18th, 1980. Mount St. Helens, when it failed, The image that you see here, which is done in black and white, was taken shortly after the eruption itself. You can see that the volcano in the back is no longer conical. The volcano is no longer conical because a whole section, roughly the large section of the north flank, failed and slid to the north and then bent directly to the west, coming at the camera person. Now, this is what we call a debris avalanche. How does this differ from the generic term landslide? Well, landslide is just a generic term that geologists typically don't use, but it doesn't specifically say what's moving, how fast it's moving, is it earth, is it rock, is it all sliding, is it rotating, is it flowing, is it falling? It's just a generic garbage bag or garbage can term. A debris avalanche is specifically a word given to a volcano that fails, portions of the volcano collapses, and that can occur with an eruption or without an eruption. It could be that the volcano just becomes chemically eroded and becomes weak in its center, and then it starts to fail because of gravity. Or it could be that magma is moving onto the surface and the volcano inflates and deforms in weird ways, and it becomes gravitationally unstable. In Mount St. Helens' case, magma moved up under the volcano. The lid of the volcano, the actual surface structure of the volcano, was remarkably sturdy, which kept the magma largely in place under the volcano, but it didn't balloon up like the picture we have of a balloon, this sort of round structure with the narrow thing. It actually was offset under one side of the volcano, the north side, and that caused the north side to bulge, and eventually gravity won. You see this word here, hummocks. I'll show you a better image in color later, but I wanted to put this here. A hummock is a section of the volcano that has come to rest. And in this particular case, in some cases, we can actually link it back to known landmarks. For example, on the northern slope of Mount St. Helens was a structure called Goat Rocks. It was basically a knob that people would hike to and say, oh yeah, I just went to Goat Rocks. Well, Goat Rocks, when it failed, chunks of it were identifiable. We could go, oh, that's a chunk of Goat Rocks. Like somebody had just taken a puzzle, smashed it apart, but we could go, excuse me, I know what that piece is, and I know where it goes to. The interesting thing is when you see something like a landslide, the generic visual we have of landslide of rocks tumbling down a hill. Those rocks are generally rolling, they're bouncing, sometimes they are sliding, just like a child down a slide, but many times there's actually rotational movement to them, etc. It really depends on the species or type of landslide you're talking about. In the case of Mount St. Helens and other debris avalanches, the chunks do slide like that child down a slide, and we've actually seen a chunk come to rest where the grass of the surface was still intact, as if the grass, the top portion of it, moved without really any sort of effect whatsoever. Why does this occur? Well, we talked a little bit about that. Gravity is the dominant factor in these cases, and they behave in weird ways. We could sort of visually look at the chunks and somewhat put the volcano back together. So let's look at Mount St. Helens. Mount St. Helens sits at the southern end of Washington State near the Colorado or the Columbia River, and you can see it labeled there. The red dots there represent, at least in the upper portion, this portion here, the Cascade volcanoes, which include Mount Rainier, Lassen Peak, Crater Lake, Mount Hood, etc. There are a couple other volcanoes that are listed here. They form by different mechanisms, so we're not going to talk about those. But by and large, the Cascade volcanoes form because of magma generated as a chunk of the ocean floor off the coast of Washington, Oregon, and Northern California, slides underneath, and as it melts, it generates magma. The magma gives rise to volcanoes at the surface. In 1980, prior to May 18th, Mount St. Helens was a nice conical volcano. And if you saw the lecture I had given, and you can find it on our Facebook page and on our YouTube page, if you saw the lecture I gave on misconceptions about volcanoes, this is what we would call a stratovolcano. It periodically undergoes explosions, and then what's left over is gas-poor lava, which sort of oozes out and creates a pile. So it builds itself up over time into a conical pile. When Mount St. Helens blew its top and a whole section of the volcano, the north section, failed, what you're seeing in the lower left-hand corner is what Mount St. Helens looked like in 1980. Right? We say Mount St. Helens now has a crater at its summit because it really does. You have this whole horseshoe-shaped crater at the top of Mount St. Helens. And we're going to talk how it went from cone to that. In late 1979, there were earthquakes around Mount St. Helens. The earthquakes were about magnitude 4.0, and we don't have time to get into the exact nature. I'll do a video later on what the numbers for Richter scale means here. But a 4.0 is something that most people would absolutely feel. Unless you are fundamentally an insensitive person or sitting on something really cushy, you're going to feel that. But you'd have to be pretty close to the volcano to actually feel that. It would panic people if they were close to the volcano, but if they were farther away, say 10, 15, 20 miles away, they might not feel it. I got to experience about a 4.5 magnitude earthquake in Peru, and I was sitting in my bedroom at the time, and suddenly the bed starts thumping against the wall, and a water bottle that I had started rattling. The picture started rattling, and I freaked out because I went, this is a bed, and I didn't put a quarter in it. The bed started to move, and I ran downstairs, and I go, terremoto, terremoto, earthquake. And they went, temblor, what was the word that they used? They used the word for tremor. But it was sort of this generic, they'd experienced it before. Sure, it was something that you could note, but it wasn't necessarily dramatic. Minor eruptions did happen at that time in late 1979, but mostly what that was steam and old ash. It was a volcano that was releasing some gas that was building up underneath. And that gas, as it came out, would blow some of the old particles at the surface up into the sky. But what started to weird out people is in early 1980, a giant bulge forms on the northern slope of the volcano, and it is bounded by a fracture that is almost a mile long. So if you would look at it, you'd get this curved fracture that went around the top of the volcano, and craters developed at the top. Geologists in late 1979 and early 1980 said the biggest dangers should be from melting glaciers, because the top of Mount St. Helens was snow-covered. Why? Steam melts glaciers. Glacial meltwater, water, mixes with ash and creates mud. So the biggest dangers would be mud flows. And they did say, sure, sections of the volcano may collapse, but that was our more traditional landslide or mass wasting, some small rock falls in the volcano. They did not expect the whole section of the volcano to collapse. They also figured that if there is ash, even though it's just old stuff being blown about, there could be air traffic accidents, because airplanes are fundamentally just big vehicles with air filters, and they can be affected when that air filter gets clogged. So they instituted a 5-mile radius no-fly zone around the volcano. So the date didn't come out very well here, but this is March 27th, 1980. March 27, 1980, the volcano was largely still covered by snow. You can see cracks on the snow at the top. This is because the volcano is flexing underneath and is creating cracks in the surface material. A crater developed near the summit of the volcano, and you can see some darker colored material on the snow. That's that ash that the steam lifted up and just sort of tossed out onto the surface. Geologists were able to sample that material, and what they said is, this is not new ash. And the reason why that's important is because if all it is steam, many volcanoes will release steam, but not actually have what we think of as that giant explosion with the cone and the cloud that comes out the top. So all this was a volcano that was essentially blowing the dust off the surface. Had they been able to detect new ash, as in lava had erupted and was being tossed out, that would be problematic, because that would be a fundamentally more active system than just, say, steam. Within 3 days, almost all of the snow at the top was covered with ash. The bulge, which you'll see here better in a little bit, this bulge was on the north flank of the volcano. If you notice, there are 2 craters, not just one. A new crater developed, and eventually these joined each other, and a crack developed on the top. I said it was about 1 mile in length, and it curved around the top of the volcano. So what are we looking at? North here is to the right, south is to the left. And we see the fractures, we see the bulge. As the bulge grew bigger, they had small eruptions, all old ash, and earthquakes. The avalanches of rock and ice actually got bigger, and the geologists said they were football field size. That's a pretty sizable amount of material to move down the slope of the volcano. But still, that made sense. Earthquakes, jiggling loose rocks that would fall down. Here's the problem. By April to May, the bulge was growing nearly horizontal at 2 meters a day. 2 meters is about 7 feet, which meant that that bulge was growing outward toward the north at 7 feet. So the entire side of the volcano was swelling. The total deformation of the north side of the volcano was about 135 meters. So if you do the math, 135, 270, 400, between 400 and 500 feet that the side of the volcano actually had swollen. So what's the problem? Well, they saw standing water in the crater, mud flows and the rock falls were confined to the volcano, but they realized that that couldn't last because gravity was going to win over that bulge. So let's look at a different view of it. This is from a ski run, the parking lot from a ski run looking south at the volcano. And as we look south, Goat Rocks, that thing I mentioned at the beginning, is on the left-hand side. This is Goat Rocks. This is the bulge, and the ground looks stretched. It is effectively stretch marks. The volcano is going to give birth to something horrible, potentially. And what you see coming out of the top, if you notice, this is basically white. This is steam, not actually ash. And there is a little bit of particle matter in here. Some of that is that ash, basically old stuff in the volcano, which is being chucked into the sky. Okay? Now, let's look at the actual summit. This is getting into April. The two craters at the summit merged. So now we have this one sort of almost infinity sign-like or figure eight, a series of craters that they connected. The white cloud that is coming out, that's just steam. There's no ash there or very little ash. And if it is, it's just old ash, old dust in the volcano. And the white stuff toward the back, these are glaciers. So some of the glaciers had already melted, but others were still on the volcano. So this is steam. That crack developed so large, and the top portion of the volcano, the northern end of the volcano to the right of the image, started to shift down. Why? Because everything is stretching. So as it stretches, some parts break and slide relative to the rest, created what we would call a scarp, a big cliff. And that cliff represents those stretch marks, sort of like if you, nobody does this, but this is the first visual I can think of. You take cake and you would pinch cake and it would break off from the rest of the cake, right? We'd see the stuff that we pinched and the rest behind, right? Because everybody and their brother is clearly pinching cake, right? Within a month, this is what it looked like. There's Goat Rocks again on the left, right here. This is our bulge. And the way that we knew that it was growing about 7 meters a day, 7 feet a day, sorry, was because we had a scientist, in this case, Dave Johnson in the image, who was working. He didn't have his PhD yet, but he was working on it. He was a graduate student that was really interested in volcanoes, helped the USGS here. And what he had done is he had set up a tripod, and they had a laser mounted to that tripod. That's what he's looking through. There's basically a little telescope and a laser, and the laser would send a signal that would beam off the volcano and come back to him. And when it would do that, he could measure distance. So he was figuring out the distance between his laser and the volcano's surface each day. And each day we could see that it was about 7 feet difference, that the side of the volcano was inflating. If you've ever been to Mount St. Helens, that ridge that Dave Johnson is standing on is now called Johnson's Ridge, because Dave Johnson was killed in the May 18th, 1980 eruption. And the story goes a little bit like this. Dave Johnson had spent an incredible amount of time monitoring the volcano from this parking lot of a ski run, looking at the volcano with his laser. Closer to when the volcano erupted, and we didn't know when it was going to erupt, Dave Johnson wanted to go back. He was going to work on more of his PhD, go back to school. And he had been replaced by somebody else. Well, the day before or 2 days before the eruption, the person who had replaced him needed to go back to defend their PhD. And they said to Johnson, hey, could you go back and take over monitoring duties? And Johnson said, I don't feel really comfortable about this. I feel something like, you know, that sort of Star Wars, I have a bad feeling about this. But he'd done it before. So he said, sure, I'll go back and do it. And then on May 18th, it erupted. And we're going to talk more about Dave Johnson here in a minute. When the volcano erupted, we know it erupted at about 8:32 a.m. on May 18th. And it was preceded almost immediately by a magnitude 5 or greater than 5 earthquake. That is something that you would absolutely feel if you were close by. A husband and wife team in I think a twin engine plane was flying over nearby. They weren't directly overhead, but they were flying around the volcano. And they said the entire north slope of the volcano seemed to liquefy. And why did it liquefy? Well, it didn't really liquefy, but what they were seeing was this. When the volcano started to move, the north slope of the volcano started to move, it effectively had the appearance of somebody shaking out a carpet. So the volcanic surface started to vibrate, and as it vibrated, it kicked dust into the air, which made everything look cloudy and diminished in visual appearance. So it looked like somebody just kicked up an old dusty rug. The north slope failed in 3 giant slabs. The first slab shifted down the side of the volcano, and once it got a good distance down the volcano, then another slab closer to the summit started to move, and then a third slab taking basically back to that scarp started to move as well. So why is that important? Well, obviously we have an avalanche on our hands, and that's problematic. When the first slab started to move, we didn't really have that much of a problem because we're like avalanche. Geologists at the time said, well, if we do get an avalanche and we do get an eruption, volcanoes blow up, right? Our classic picture, think about how we drew it as kids. We have our little conical shape and then we draw the cloud that erupts out on top. But what happened is when that second slab started to move, the magma that was building up under the volcano was uncorked like a champagne bottle, and all of the gas near the surface was immediately able to grow in size. So we had this sort of like immediate frothy soda, like we'd shaken up a soda and then we violently pop the top. So that depressurization allowed a massive explosion, but because the side of the volcano that contained that magma was moving downhill, instead of it firing upright, it fired out at an angle about 30 degrees above horizontal. And I tell my students, the easiest visual for that is if you remember the old Wile E. Coyote cartoons or the old Marvin the Martian with the cannon that's pointed upright and then something happens and the cannon starts pointing at an angle. That's the visual that we actually have. So when it failed, here's the problem. We had a collapse. And I hope this video should load because if I'm sharing my screen, it should load. This is a series of stills taken from the volcano at the time and sort of put together in a loop. And I'm going to let it play and then I'm going to go back through it. I'm going to talk about it. So this is just still sort of done like a digital flip book. If we look at this again, one section, the first slab starts to fail and it moves downhill. And we start seeing the eruption. But then another section starts to move after it. And as that occurs, the path of least resistance is now out at an angle. So instead of it blowing up, it blows out at about 30 degrees to the horizontal. And we can see that right here. It starts blowing up, but then we get a section that moves. And now it is moving outward at about 30 degrees to the horizontal. A third slab does move. It's harder to see, and in some videos, they actually run longer than the video I'm showing here. And we can actually see that third slab, but for our purposes, it doesn't necessarily matter. So, the hazards itself. The avalanche involved 2.8 cubic kilometers of material. Most of that was old section of the volcano. Geologists have a hard time when they're talking big scale because it's not something that we're familiar with. So we can show with our hands that a foot is about if I can get my hands in the frame, I'm still learning, right? About this big. So this is a foot. So a cubic foot would be something like this, right? About the size of an average cooler, like to go to the beach or something. A cubic meter is about 9 of those, because a cubic meter is about 3. So actually about 27 of those. 3 times 3 times 3. It's 27 of those coolers stacked around. That's an enormous section. If you say, well, 27 coolers doesn't exactly fit in my memory. I had a professor in high school who was teaching me calculus, and he said this: always attempt to take something that you know and relate it to something that might be hard to figure out. For example, what is a cubic meter? He said, well, a cubic meter is a horse. And we all looked at him, we're like, how is that a horse? That's not a cube. And he goes, well, if you take the head of the horse and fold it under, and the legs and fold them under, you can imagine the barrel of that horse. That's about a cubic meter. Well, this is a cubic kilometer. This is 1,000 times that on a side. So geologists come up with these numbers, and then we go, well, how big is that? Well, if you imagine a cube about this big, this would be the Eiffel Tower for scale. So imagine a cube, right? If you did, say, a Rubik's Cube, which is this big, then the Eiffel Tower would be like this. So that is a massive amount of material, and Mount St. Helens was considered a medium-sized eruption. It fell in sections, moved at speeds up to 80 meters a second, which is about 250 feet per second. Right? It broke up into sections and followed valleys and low spots in what we would call lobes. One of the lobes went into a popular fishing area on the northeast slope of the volcano called Spirit Lake. And when it displaced the water, it created a wave that was almost 800 feet in height. And it raised the lake level by about 60 meters, which is about 200 feet in height. Why? Because it just filled the glass of the lake. At that point, there was a popular lodge on the lake called Spirit Lake Lodge, and it was owned by a man named Harry Truman, not President Truman, but Harry Truman. And Harry Truman was sort of the bad boy of the volcano because he was some 80 years old, and he said, they're evacuating the volcano and putting up these cordons, and they're not going to evacuate me. I've always been a part of this volcano, and it's always been a part of me. And he was right, because he was buried by the debris avalanche. It traveled 22 kilometers, which is about 15 miles down the North Fork of the Toutle River to the northwest of the volcano. And I'll show you a map that explains this. It buried a humongous section of terrain. 60 square kilometers is about the size of McKinney, what I showed you at the beginning, to an average depth of about 150 feet, 45 meters. It took out 32 kilometers of state highway, 7 bridges, and all structures around Spirit Lake. So consider this. This is the devastation given by Mount St. Helens, and we're going to talk about each one of these in parts. The debris avalanche, the sections of the volcano that failed, are shown by the slanted lines. The North Fork of the Toutle River is shown there, and we can use the scale to figure out distance. If you watch the video that I had on volcanoes and misconceptions, pyroclastic flows are those dense clouds of gas and rock that we see roiling down explosive volcanoes. You've probably seen a famous video of this volcanic cloud rolling and a truck running, driving away from it with somebody running in front of that. That's Mount Unzen in Japan. That cloud can reach speeds of 100 to 150 miles an hour and be 1,200 degrees Fahrenheit. If you've seen the movie, the second Jurassic World movie, and you see Owen Grady get caught by the cloud, and Owen Grady, you know, somehow survives the volcanic eruption, he is absolutely and fundamentally dead. There is zero way that he could survive that, even if he jumped into the ocean. But in those cases, those pyroclastic flows were contained within, say, 3 to 4 miles of the volcano itself. The mud flows, which we'll talk about later, traveled vast distances. They go fundamentally off the camera here. But the other thing on here is this sort of light orange yellow color, which is called the lateral blast. We'll talk about, that in a minute, because it is ridiculous. But look at the debris avalanche that travels down the volcano. Johnson's Ridge was placed just outside of the debris avalanche path north of the volcano, north of the pyroclastic flows. And if you've been there, that's the viewing platform for Mount St. Helens today. This is the debris avalanche deposit, a picture taken shortly after the eruption. And it is an interesting picture for several reasons. One, we can see the chunks of the volcano as these conical piles in the foreground of the image in the center. These are the chunks of the volcano that broke from the north, slid down in place and came to rest. And in some cases, we could backtrack and go, oh, this is part of Goat Rock, for example. They included the volcano, the soil, the trees that were on it, and the glaciers. And that proved a long thorn in the side of Washington State because as the glaciers melted, they could generate mud flows. Mud flows are shown here in the center, this sort of a brownish mass in the center and like almost floodplains on the sides of it. If you look up here also, you don't see any trees aside from right up along the northern background, right? Or I guess just the background of the image on the left-hand side and then the center, because when the volcano erupted and that blast came out at an angle close to the horizontal, it just stripped all of the trees off. And that is what killed Dave Johnson. Dave Johnson, when he saw the volcanoes start to fail, he had about 6 seconds before he died because the eruption cloud traveled out at about 400 miles an hour. And we do have a record from him because he was using a ham radio to communicate with Vancouver, Washington. And he reported, Vancouver, Vancouver, this is it. And the radio clicks off. And a few seconds later, he goes, Vancouver, Vancouver, this is it. And he dies. When the cloud traveled outward past him, even though the first thing that failed was the volcano in this debris avalanche, because it uncorked the champagne bottle, that cloud was actually much faster than the movement of the chunks of volcano. So in the near surface toward the volcano, debris avalanche, cloud on top. Farther out, cloud, debris avalanche on top, because this giant blast surged out from the volcano. When it killed Dave Johnson, it removed all of the trees, all of the vegetation, all of the soil, everything down to bare rock, and we found a piece of his trailer about the size of a standard monitor, something like this. That's about it. To the northeast was a ham radio operator, former military guy named, I think he was George Miller. And George Miller had more time to survive, and he said this: the camp to the south of me, which would be Dave Johnson, the camp to the south of me has been overrun, and I'm going to back out of here. And then the radio clicks back on a little bit later, and he says, I'm not going to get out of here. It's going to get me too. Now, in those days, like, why don't you freak out? Well, what good would freaking out do, right? It's the resignation. It's not like you have some idea that you're going to, there's not a reason to panic in that scenario. That said, amazing, the story of that. And it is amazing the sort of aplomb they had in the face of imminent destruction. So let's talk about the directed blast itself. It overtakes the avalanche, travels at a speed of about 430 miles an hour, and it reaches 50 kilometers in 13 minutes. It did slow down, but that means on average it was going about 200 feet per second for 13 minutes. It covers a humongous area, about 10 times the size of McKinney, and 1 centimeter doesn't sound like much, but when it's covering that area, that's incredible. Close to the volcano, most of the trees were uprooted or snapped off. In the few kilometers closest to the vent, they're just absolutely blown away. And I'll show you a picture here in the background. After the destruction, we could go out and look at the tree blowdown and figure out which direction they traveled. So let's look at the blast itself. Around the volcano, you can see here lines going from the north, and I'm pointing at my screen, like of course you can see me pointing at the screen. You can see here, I'm still learning. You can see here lines radiating out from the volcano, but in the area close to the volcano, the trees were just fundamentally removed. Johnson's Ridge was somewhere around here. When the cloud rolled out from the volcano, actually it was back about here. When the cloud rolled out from the volcano, it removed the trees, but farther out, it just flattened the trees, and we could tell the direction that the cloud actually traveled. This was what we called the directed blast zone, because this is just a blast that goes out and flattens everything. But as we went farther away, now the blast started to be affected by valleys and low spots. So we would call that the channelized blast zone. And we get really far out, all it does is burn the trees, but not actually flatten. Here's an example of what the trees look like. If you've ever taken a toothpick and you put the toothpick in your mouth, you know that over time you can bend the toothpick and you can get almost a half moon shape, a crescent shape. And you can't get that with a dry toothpick. This is exactly what happened here. As the blast cloud went out, it heated the sap and the water in the trees, made the trees flexible, and they just laid down. One of my favorite stories that comes out of this was a family who was camping, and the USGS and the National Forest Service had put a cordon around the volcano, an area of about 5-mile radius, where they said, well, you just can't go because it's not safe. Because even though they didn't know exactly the nature of the eruption that they were going to get, they just said, well, it's bulging. There's something bad that's going to happen, and we don't want people nearby. So this family was much farther away than that, but we didn't expect the cloud to come out at an angle. And they said they heard a noise, they looked up at the volcano, and they saw the forest coming at them like spears. And the cloud rolled into their camp with this forest of green spears. And they said just before it hit them, all of the trees stood up and went back toward the volcano. And when I heard that, I'm like, that's insane. And scientifically, why? Why does that make sense? If an explosion is big enough, a vacuum is created near the center of that explosion. So as the trees went out, eventually the sucking force backwards to the volcano overcame the outward force. And so the trees stood up and went backward toward the volcano. So even though they were not crushed by trees, they absolutely had to go to the laundromat the next day. All right. Now let's talk about the mud flows. A mud flow is just a collection of debris, sand, silt, clay, mixed with water. And depending on the exact mix of that debris with the water, it's either very slow moving, very chuggy, but very dense and could be very erosive, or could be closer to water and so flows more like water. A volcanic mud flow is called a lahar, L-A-H-A-R. And mud flows do an incredible amount of damage. When they are generated, they can do an incredible amount of damage because they can travel generally farther than any of the other materials generated by the volcano. So in this particular case, what you're seeing is a vehicle that was buried by a mud flow, blew out all the windows. And then the water dries out, and now you're just left with this pile of mud. The mud flows were long-lasting, prolonged hazards in the volcano because glaciers were in the avalanche deposits, the debris avalanche deposits. So here we see Mount St. Helens post-eruption. The volcano lost 1,300 feet of its height. It's no longer a cone. We have a crater. I think this picture is taken from near Johnson's Ridge, looking at the volcano. Here it's still producing steam, but that dark material that you're seeing there, that's lahar, that's mud flow. So we had a problem for a long period of time. In the river, the North Fork of the Toutle River, which flows into the Columbia, the material, the avalanche material was saturated by those glacial blocks. And as they melted, they created lahars, which were able to travel 120 kilometers distant, about 90 to 100 miles, to actually reach the Columbia River. The flows reached really fast speeds, and the total amount of material was 50 million cubic kilometers. So nearly, we're talking getting closer to that, 50 million cubic meters. We're getting closer to that cubic kilometer number. And one scientist did the math here, and he said it would be like a football field filled 350 miles deep, you know, a number that everybody seems to understand, right? The mud flows had this problem. Levees were around the Columbia River anyway to prevent flooding on floodplains. So they came within inches of going over the top of the man-made levees, which would have caused dam failure-like scenarios with mud flows. It affected a hydroelectric dam. So the hydroelectric dams on the south side were actually drawn down so that the water that would normally be there wouldn't be displaced by the mud flows and potentially destroy the entire dam. but the hydroelectric dams contain the mud, and then we had to pump out, remove all that mud, because without that, then the hydroelectric dam loses capacity. It blocked shipping lanes in the Columbia River. It destroyed huge amounts of railways and roads and bridges, destroyed waters and sewage systems. Why? Because if they take the water from the Columbia River, now there's a serious problem. And they threatened a 1 million kilowatt hour nuclear power plant. Why? Because that nuclear power plant used water from the Columbia River as part of its cooling mechanism. And now if the river is full of mud, they can't easily do that. So what does it look like after? On the left-hand side, we can see how deep the mud flows got in certain spots. That's all dry now because we can see chunks of mud sitting on top. On the right-hand side, we can see that as the mud passed, in some areas it was comically deep, and then it drained away and it left a mud line like a bathtub ring on the trees. And if this guy is, say, 5 feet tall for scale, 5, 10, 15, 20 to 25 feet of mud, and he's also standing on mud, so 20 to 30 feet of mud rolling through the region, and you can see the mud on the trees in the back. The volcano also had a cloud that went up into the sky, a classic picture of a volcanic eruption. The volcano dumped ash at depths of up to 20 centimeters, which is about 10 inches. So if you think about a ruler, right, this is 10 inches. So the ash actually blanketed the region in certain areas up to 20 centimeters or 10 inches. An average house roof, even a modern reinforced house roof, can only handle about 6 inches of ash. And the reason why, it has the same density as sand. So if think about a bag of play sand, when they sell it in that long brick, but that brick is about 6 inches thick. So imagine putting that on the roof of your house everywhere because it blankets it like snow. No wonder why the houses collapse. The biggest danger was to aircraft from the ash because ash air filters, they don't mix. So they had to close an aircraft corridor around the volcano, and that shut down some airports for over 2 weeks. One of the crazy stories is, though, that it actually affected the Yakima sewage plant, because what a sewage plant does is they take in the water from a whole bunch of local municipal pipes, and they filter the water, and then they discharge it back into the river. Well, this one, they had so much problem, they actually had 4 days where they had to pump effectively raw sewage into the Columbia River. And we had huge areas, 2,900 kilometers, almost 2,000 miles of highway in Washington state that were closed for a week. The cloud was contained largely to Washington state, Idaho, and Montana, but a thin dusting of ash covered Colorado, Wyoming, the Dakotas, western Nebraska, and then because of the vagaries of the atmosphere, it actually lifted and fell a little bit in Oklahoma. That is ridiculous. Now, if you look at the areas that were affected, you see Mount St. Helens and then the vagaries around Ritzville, etc. We have the 2 to 5 inches, but some areas got up to locally about 8 to 10 inches of ash in very limited areas. This is May, so you'd expect when you look at that, it's like some sort of snow on the ground. That's all ash. So what were the long-term hazards and effects? Well, one of the rivers that extends westward from the volcano is called the Cowlitz River. The deposits in the Cowlitz River actually reduced the depth of the Cowlitz River by about 10%. This would increase the risk for flooding because if I have a river that has a bunch of sediment in it and it no longer has as much depth, well then a lesser amount of rain could lead to flooding. The streams generated by the avalanche from the glaciers melting created mud flows for a long period of time, but also streams, naturally occurring streams that had been in the area before, if they were dammed by the avalanche itself, now we have lakes that in some cases the USGS had to monitor and keep for a while because they risked having floods that would come down. Why? Stream channel, plug at the end, water backs up behind it as a lake. Well, you never wanted that dam to happen, but if that dam should fail, all of that water spills, like we just saw in Michigan, sort of an earthen dam created by the volcano. One of the classic pictures showing the mud flows and people seeing the erosive power of the mud flows. If you've seen the movie Dante's Peak, the visuals of the mud flows just churning the logs and rolling down, and knocking out bridges, incredible. That's a pretty good representation about what a lahar would actually look like. 57 people died in the disaster, but some of the people, note the statement, some of the people who died, they died because of being at the wrong place at the wrong time. They didn't expect the volcano to erupt the way that it did because geologists said volcanoes blow up, not out the side, at least not in this way. Some of the people were outside the zone of exclusion, but because the blast went out at an angle and went much farther north than we had anticipated, now we had a problem. But there were some dumb people that came to the region. People were getting a kick out of this. If you've ever seen Close Encounters of the Third Kind, people figured out ways of evading all of the protocols, all of the cordons and roadblocks that they'd set up. People were getting a big kick out of it. They showed up to sell t-shirts that said, "I lava you," and Mount St. Helens is a pain in my ash. Reporters often outnumbered the locals that were there. Too many trails were there to guard, so people actually climbed the volcano and actually looked into the crater. People sold maps to tourists showing them how to get around the roadblocks. There were 3 people, I think, that were trapped on the volcano, and the only way that we even knew they were there is one of them happened to have an orange hazard triangle. And so as the helicopter flew over and just saw an absolute devastation, then they happened to go, well, that's orange, and orange is an unnatural color. In one time, one of the afternoons before the eruption, there were 70 aircraft in the volcano in the volcano. They were in the volcano. They flew around the volcano, and so we risked mid-air collisions. Why? Why were people so captivated by it? Well, first of all, it's a volcanic eruption. Second reason is the way that we tended to think about volcanic eruptions is this. Volcanic eruptions were another country's problem. Sure, we had Hawaii, but that's a sexy volcano. The explosive ones were other people's problems. Ecuador, Peru, Indonesia. We didn't think about them as an American problem because the last major eruption had been 100 years prior. So in this particular case, because news reporters and locals were able to drive to it, they didn't have to fly to some foreign country. They didn't have to fly to an island that was owned by the United States, like Hawaii. They could drive to it. So everybody wanted to do it. And so you had all of these people that wanted to fly to the volcano, wanted to be part of the pageantry of the eruption of the volcano. We even had one guy, a rock star, flew in wanting to get a picture of the volcano erupting in the background for his album cover. I don't know. I joke to my students, I don't know. I could believe it's Ted Nugent. That's something I could imagine he would do. There were vendors. There was Harry Truman on the volcano, and Harry Truman, when he had his attitude of, you're not going to get me off of the volcano, that encouraged other people to actually stay. Or to come when they weren't supposed to be there in the first place. Now, 2 little funny stories about this volcano, and I think then we'll end here. So the geologists, because it was such a crazy event, the reporters wanted to see the geologists. They wanted to constantly interview them. So the geologists felt harried by the reporters. Let me move my video camera here since I'm talking. They felt harried by the reporters, and they said, we never get a moment's peace, right? We're just always hounded by the reporters. So as the event kept going, think about it. We started seeing signs of activity in 1979. As we moved into 1980, as the problem just kept going and kept going, then more and more reporters came, more and more people like, when is it going to erupt? In other words, it was like they were hoping that it was going to erupt because they wanted to be there for it. The geologists, eventually, they got tired. They were just like, we're exhausted. We need to do something for ourselves. So one of the geologists, one of the lead geologists, decided that he would attempt to cook a pig in the pyroclastic flows. They were still hot. So he got a whole bunch of, he got a pig, a whole pig, banana leaves, a whole bunch of spices, sauces, other things to dress up this pig. And he wanted to have a pig cooked in the volcano. He called it the PPE, the pyroclastic pig experiment, but they never used that term over ham radio because they knew the media would be listening in. So they called it the PPE, the PP experiment. So the media didn't know what was going on, but they knew that geologists were doing something. So the head geologist sent everybody out to find places to bury this pig because it needed to be a certain temperature. Well, he said that meant that over the ham radio, people were just calling out locations and temperatures. Finally, they found a place. They bury the pig. They go back to check on it 2 hours later, and it wasn't hot enough, it turns out. And now this lead geologist was like, you got to be kidding me. What started out to be a lark for me to try and calm everybody's nerves has turned into its own stressful situation. So he sends people back out to find a new location, and everybody's calling out locations, but he's just getting stressed out. So finally, when they find a location that's good enough, he's heard over the radio shouting, "Bring up the effing pig!" The media did not know for 20 years what had happened there because everybody just shh. He said, because he realized that regardless of how stressed out they were and how good of a job they'd done, the media would see it as a waste of taxpayer money. Never mind all the amazing stuff that happened. They went, it'll be a waste. He said, so we waited about 20 years until nobody cared. He said he toyed with the idea of submitting the recipe to the lady, like some Ladies' Home Journal or Red Book or something. And he said, but he figured that would probably get him into trouble. The other funny story that comes out of this is Dave Crockett. Dave Crockett was a reporter that went to the volcano to witness the volcanic eruption. I'll put this in a link in the description of the YouTube page. He said, I went to the volcano, but when the volcano, he said, I knew I needed to be here because this was going to be the story of the century. When he drove up, the area where he drove up to film the volcano was affected by a lahar, and it washed out the road on both sides of him. So there was no way that he could get out by car. So he decided he would walk uphill to get better pictures of the volcano. He said, well, if I'm here, I might as well get pictures of the volcano. Well, when he walked uphill, then eventually the ash cloud started to roll in and settle down over the region. So like smoke from a fire, eventually it became really hard to breathe. And so he couldn't really find a way out. Now, in the smoke from a fire, what do we say? Get on your hands and knees, crawl out, get as low as possible, try and get out of the house. Well, he actually had to walk uphill to the only light that he can see on top of a ridge, because the way the cloud settled, it settled in this valley that he was in, and the only light that he could see was on top of a ridge. So if you watch his video, he describes how his experience was hell on earth because the cloud burned his eyes, burned his throat, clung to him. And there's a point in that video where he says, he said, I never thought I'd believe this, but right now I honest to God believe in death. And then there's a pause, and he says this, I have the wrong idea about this. I have to get a better perspective. This is going to be a hell of a story to tell my grandkids. And then he said the ash started to blow out, and he said I could see better, and I just realized I was going to be okay. It's one of those things that when you are caught in it, we see this in movies, when somebody's caught in a disaster, they like The Rock or something, and they overcome the situation and machismo, etc. That's not what we need. We just need the person to go, well, this is life now, right? And if they do that, there's no point in getting bent out of shape. I will end with this. One of my favorite comments comes out of the TV show Babylon 5, and it's Bruce Boxleitner's character. And he says this, if you're falling off a cliff, you might as well try to fly. You got nothing to lose at this point. So Thank you for listening to me bloviate and talk at length about Mount St. Helens. If you're interested in this, once I post this video this Friday, I will record another lecture that will be live. I will record another lecture on plate tectonics, talking about the science of plate tectonics. It'll be on our YouTube page. We are Blackland Geology and Reptiles, and you can see us on Facebook, on YouTube, or on Twitter and Instagram. Find us. If you like what you saw and you want us to give a lecture for you, we're doing discounted rates because we obviously can't meet people in person now. We do everything from biology to environmental science to geology to natural disasters. My wife and I have 20+ years of experience as educators. So if you're interested, come talk to us. And thank you.